So in this video we are going to talk about max power transfer. And what of course I mean by max is maximum power transfer. And apparently I can't even spell transfer correctly. Transfer. Alright. So the reason we want to talk about this is that power is what we need to do work. And I'll put work in quotation marks because depending on what it is, this might be, for instance, turning a crank. You know, if you're thinking about like a electric motor, just a simple DC motor, yeah, you put a voltage on it, but there's a voltage and a current going through there, so the motor is absorbing power, and that's the power that it's absorbing is actually what's turning that crankshaft on that DC motor. And a classic example here is if you just have a simple 5-volt DC motor. I can connect, and I believe your DC power supplies might be able to do this. If you have a DC power supply set at 5 volts, the motor may not run. And at first thought you're thinking, it's like, well, wait a minute, it's a 5-volt DC motor, it needs 5 volts to run, so I attach 5 volts to it, why doesn't it run? Well, it needs current as well. Some power supplies allow you to control the amount of current let out. So that's how I can have a DC supply that I connect to a 5-volt motor and have it not turn. Is I could crank it all the way down, so yeah, there's 5 volts there, and if you hooked a multimeter up, you'd still measure 5 volts, but if I crank it down such that 0 current is allowed through, well, there's no power getting to the motor. There's still 5 volts on the motor, but there's no power because there's no current. And remember, it's power is what we need to do work. Power is what we need to turn the actual crank. So we actually need both voltage and current in order to do things. So, of course, if power is what turns the crank, we want to think about, well, I want to be able to deliver the maximum amount of power then, because I want to be able to do, quote, the maximum amount of work. And so that brings up a question is like, well, how do we design our circuits, or how do we design our loads in order to obtain maximum power transfer? So let's first examine this with a very simple circuit here. And this is going to just be a 10-volt power supply. And this is going to be a 2 kilo ohm resistor, and then a 10 kilo ohm resistor, and this is what's going to be my output. So this is what I'll connect up here, and what I'm going to be connecting up, I'll put it in red with dots here, is I'm going to be connecting up a load here. So this load is just a resistor, but this resistor, I mean, you can use these honestly to model a lot of things. You can think of a motor as just a resistor. In fact, you can think of a speaker as just a resistor as well, as ways to model them. And so we're going to look at this circuit here. So first off, we're going to just simply, what is the power when there is no load? And when I say power, I'm going to say output power. In other words, the power across that 10k ohm resistor, because that's voltage out there. Well, This is a very simple circuit to analyze. You could, because we're looking at just this 2 kilo ohm and 10 kilo ohm in series, so we could just do a simple voltage division to get that V out is going to be equal to 10 kilo ohms over the series combination of 2 kilo ohms plus 10 kilo ohms times my input voltage, which is 10 volts. And if we do this computation, you get roughly 8.33 volts. And then just using our equations for resistors for power, the power on the output would then be voltage squared, so 8.33 squared, divided by the resistance, which is 10 kilo ohms, which would equal, here, let me just do that real quickly. And you would end up getting, if I did my computations correctly, 6.94 milliwatts, approximately. Okay, but now let's attach a load. So what is the power across the load if RL is equal to, let's say here, 10 kilo ohms? And so let's redraw the circuit so we can see what we have here. So this is the circuit I have here. And now what it's wanting is the power across this load here. So we're wanting to know what is the power. I'll say plus minus V out, and we want to know what is the power here. When I attach the load. Okay, well, there's lots of ways you could analyze this circuit. The easiest way would be to figure out V out again, and then just do V out squared over 10 kilo ohms, because again we're just looking at this resistor here. Now you could do a nodal analysis where you just look at this being a node and you put ground down here and get a V out that way. That'd be fine. Some of you want to do that, that's fine. I'm going to go ahead though and notice that this 10K and 10K are in parallel. So I could redraw this circuit. So that this is 10 volts, 2 kilo ohms, and then I'm not even going to bother with the computation, but remember, if you have two resistors in parallel that are the same value, the parallel combination is just going to be half. But we also, I'll just put it off to the side here, remember that parallel combinations of two resistors can be done with R1 times R2 over 1 plus R1 over R2, R1 times R2 over R1 plus R2. Or you could do the 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. So we know that there's several ways we could do this. But we know because components are in parallel, these have the same voltage, so V out is still the voltage across this 5 kilo ohm resistor. And so now if we do voltage division here, we get V out is equal to 5K divided by 2K plus 5K times 10 volts, which doing that computation, you get approximately 7.14 volts. Now, if we're doing the power here, remember, we're not going to use 5 kilo ohms because we're looking back at the original circuit here. This is my load right here. Now, we know that V out that this is equal to 7.14 volts. That's what we just did down here with our analysis. That's what we did right here with our analysis. But we're looking at the power dissipated by that 10K. In other words, what's getting to the load. And so then we would have the power to the load is 7.14 squared over 10 kiloohms. And if I do that computation, what do we get here? We get 5.10 milliwatts. So what we notice here, you can notice right now, I want to point out two things. When we didn't have a load attached, the power dissipated essentially where we'd be attaching the load was 6.94 milliwatts. So we didn't get 6.94 milliwatts on there on the load. We only got 5.10 milliwatts on the load. And so this is what's sometimes referred to as a loading effect by the resistor. So you're like, okay, well, that's great. But let's look at this with another resistor value here. And let's go ahead and do this computation one more time. Part C. And this time we're going to make the load resistor 5 kiloohms. Yeah, we'll go ahead and do 5 kiloohms. That's fine. We'll just do some approximation values here. And so I'll redraw the circuit again. So I got 10 kiloohm, 5 kiloohm, 2 kiloohm, 10 volts. Now I'm going to analyze it. Well, actually, this time we'll go the other way, because we want to find, again, V out, because we want to know what the power for the load is, which is the power across the 5K. We'll go ahead and do it the nodal analysis method this time instead of doing the parallel combination. So this here is actually just going to be V out, because I'm going to make this ground. And then we'd have this node here equation, so we'd have V out minus 10 over 2K, because that's the current going this direction, plus V out over 10K, that's the current going down, plus V out over 5K, which is also the current going down. And so that's all of those currents, and that this is then equal to 0. And we can clearly see here, if we want to clear these fractions out, the most common number that would make sense to use would be 10 kiloohms. And if we do that, we would get 5 times V out minus 10 plus V out plus 2 V out equals 0. Combining like terms, we get 8 V out is equal to 50. And so V out would then be 50 divided by 8, of course, which is 6.25 volts. So now let's compute the power for the load again. So the power for the load in this case would be 6.25 squared. Now notice here, we might say, well, wait, this power is going to be lower because look, the voltage is lower. I've only got 6.25 volts as opposed to 7.14. But we have a different resistor value. In this case, we had 10K. Now I'm only dividing by 5K because I've reduced my load resistor. And if I do this here, 6.25 times 6.25 divided by 5K, we end up getting 7.8, rounding, 7.81 milliwatts. Well, wait a minute. That's higher than what I had with the 10K. So what we've been doing in this video is we've been trying to investigate what happens when you attach a load to your circuit. And so the question we should wind up with at the end of this video, and we'll answer it in the next video, is what should we set RL to be for maximum power transfer? That's what we should ask ourselves, and that's what we're going to answer in the next video.